Hi there. In this video I'll be answering a question on the gravitational force between two objects, the Earth and a satellite in orbit above it to be exact. The question builds to a crescendo with a nice bit of problem solving at the end. This question is from the 2019 CFE Higher paper and it goes like this. A communication satellite orbits the Earth at a height of 36 times 10 to the power of 6 metres above the surface of the Earth. The mass of the Earth is 6.0 times 10 to the power of 24 kilograms and the radius of the Earth is 6.4 times 10 to the power of 6 metres. Part A then asks us to determine the distance between the centre of the Earth and the satellite. Before we do that, let's add some colour. These exam questions are so dull. Do your head in. So that's a nice easy question. And if you didn't realise, it's setting us up for part B of the question, which we'll see later. To find the distance from the centre of the Earth to the satellite, we'll just add the two distances together. The radius of the Earth, which is being drawn now, plus the height of the satellite's orbit above the Earth's surface. That gives us 6.4 times 10 to the power of 6 plus 36.0 times 10 to the power of 36, which is equal to 42.4 times 10 to the power of 6 metres, or 4.24 times 10 to the power of 7 metres. Next up, it's part B of the question. The gravitational force of attraction between the Earth and the satellite is 57 newtons. Calculate the mass of the satellite. So if we get a little bit more space to do our working, we use this equation here, where F is the gravitational force between the Earth and the satellite. Uppercase G is the universal constant of gravitation, which is found in the data sheets, not to be confused with the gravitational field strength or gravitational acceleration on Earth, lowercase g. M1 and M2 are the masses of the Earth and the satellite. You decide which is which. And R is the distance from the centre of the Earth to the centre of the satellite, or at least the satellite's centre of mass. Now you can see why we had to work out part A of the question. Now I'm going to make M1 the mass of the Earth and M2 the mass of the satellite. So to calculate mass M2, I could divide both sides by g m1 over r squared, which gives me m2 is equal to f r squared divided by g m1. To be fair, it's probably easiest just to start with our original equation and substitute our values. That gives us this. 57 equals 6.67 times 10 to the minus 11 times 6.0 times 10 to the power of 24 times m2, all divided by 4.24 times 10 to the power of 7 squared. Even if we make a mistake, we already have 2 out of the 3 marks, which is why it's a good idea to write the equation, then substitute the values before rearranging. Next, we can multiply both sides by 4.24 times 10 to the power of 7 squared, which gives us this. We can then divide both sides by 6.67 times 10 to the minus 11 times 6.0 times 10 to the power of 24, which makes m2 the subject of the equation. We then get a trusty calculator out, plug in the numbers, and it should give an answer of 256.05 kilograms, or 260 kilograms to 2 significant figures. Part C asks us to determine the value of the Earth's gravitational field strength G at the satellite. Because I care so much, I'm actually going to show you 2 ways to work this out. The first method is to use the equation from National 5 Physics. So the weight of the satellite will be equal to its mass m2 times the gravitational field strength at that position in space. Remember as well that the satellite's weight at that position in space is just the gravitational force of attraction between the Earth and the satellite, which we were told in part B is 57 newtons. So the gravitational field strength at the satellite G is equal to its weight force, the force of attraction between it and the Earth, divided by its mass. This gives us 57 divided by 260, which is 0.22 newtons per kilogram. That's the first method. Or we could do it this way. As we saw before, gravitational field strength is equal to the satellite's weight divided by its mass. Since its weight is the gravitational force of attraction between the satellite and the Earth, we can substitute the equation for gravitational force into the equation like so. That can then be simplified to uppercase G, the universal constant of gravitation, times m1 over r squared, where m1 is the mass of the Earth and r is the distance from the centre of the Earth to the satellite. If we substitute the values into that equation, we get this. which unsurprisingly works out to 0.22 newtons per kilogram all over again. Here's the last part of the question, part D. Oh my goodness, that looks so wordy. A second satellite has a quarter of the mass of the first satellite. The distance from the centre of the Earth to the second satellite is half the distance from the centre of the Earth to the first satellite. State how the gravitational force of attraction between the second satellite and the Earth compares to the gravitational force of attraction between the first satellite and the Earth. Justify your answer. Right, we'll have to take this slowly. Let's start with our equation for gravitational force. If the mass of the second satellite is quartered, this will have the effect of quartering the gravitational force between the second satellite and the Earth, compared to the force between the first satellite and the Earth. If the distance from the second satellite to the centre of the Earth is half that of the first satellite, then r squared will be a quarter of its original value. Since this is on the bottom line of the equation, it will result in a gravitational force which is 4 times as large as with the first satellite. In other words, it's quadrupled. Of course, if the first change has the effect of quartering the gravitational force, and the second change has the effect of quadrupling it, then when both changes are made, they'll actually cancel each other out, and the gravitational force between the second satellite and the Earth will be exactly the same as between the first satellite and the Earth. We could write something like this. Quartering the mass of the satellite alone will quarter the force of attraction. Halving the distance alone will quadruple the force of attraction. That's our justification taken care of. But we'll also have to write that the force will, therefore, remain constant. Now that's a tricky question, but if you take it one step at a time, apply what you know using the equation, then it's made an awful lot easier. If you wanted to, you could also justify your answer by calculation. Substitute a mass which is a quarter of the original value and a distance which is half the original distance, and you'll find that you end up with the same force as before, 57 newtons. And that's us. If you want to be made aware when new videos come out, then here's an idea. Subscribe to the channel and click the bell icon. What's the worst that could happen? Apart from being subjected to more physics problems. Thanks for watching.